While we will primarily discuss this from Earth's perspective, this can be applied to any planet which will be having some g of its own. So because of Earth, some mass small m experiences some force. That is the gravitational force. F upon m is the acceleration A, and which is what we are calling here as g. The force that Earth applies on the mass depends on the distance of the mass from the center of the Earth. We have discussed the case of a solid sphere, the field outside it, the field inside it. And in both cases, we find that distance matters, whether inside or outside. So we expect that small g changes with distance from the center of the Earth, whether inside the Earth or outside the Earth. Let us first talk about outside. Let's say some height h, at some height h. We will treat Earth as uniform solid sphere for the sake of simplicity. For outside points, we can imagine a point placed at the center point. So the force that Earth applies on that fellow, say small m, would be gmm by the total distance square, which is same as radius plus h square. That force upon m is small g. So g is gm divided by r plus h square. Obviously, it is falling. It is falling as h is rising. So while we have this result, we will try to simplify it for not very large values of h. We will try to simplify it for not very large values of h. This is the general result. Now consider the special case. What is the special case? H is very small in comparison to the radius. Radius is 6,400 kilometers. So very small means maybe 50 meters, maybe 100 meters. Now, for that case, we can use binomial expansion. Gm by r square is g at the surface. G at the surface. Maybe we can call it g naught. This should be -2. Now, applying binomial theorem, that is negative power here. So 1 minus this, and then there will be higher powers of h by r, like h square by r square, h cube by r cube. But if we are saying h is very small in comparison to r, then imagine what happens to h square. Very, 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 very less in comparison to r square. Higher powers become less and less significant in such situation. So we are going to make this approximation. We won't proceed further. So we have G equal to G naught 1 minus 2h by r. This result is not 100% accurate. It is only approximate. Never use it when you are analyzing what is G due to Earth at Moon. Moon is so far that small h will not be very, very small in comparison to the radius of the Earth. You can't use it for that case. Yes, close to the surface of the Earth, maybe mountains, those cases you can use it. But otherwise, that's the way to go, this one. This is the way to go for such cases. Very large distance from the surface of the Earth. This is the way to go. G equal to Gm upon R plus H whole square. Any questions regarding this? If you have, then let me know, or we discuss variation with depth. Fine. So let's discuss variation with depth. Now imagine small m placed there. Now this time we can't replace Earth by a point kept at its center. That result is fine for external points, not for internal points. So how do we handle this type of situation? Let's draw this boundary or borderline, and now imagine contribution due to two masses. One mass of the Earth outside the borderline, all this, and the other one inside the borderline. For the mass which is inside the borderline, maybe I can call it M1 and that one M2, where M1 plus M2 is equal to M. For this mass M1, it's like point small m on the surface. So capital M1 can be considered as a point mass, isn't it? So force due to M1 is very easy to evaluate. How about force due to M2? What is M2? M2 is a spherical shell type of a thing. It's hollow from inside